In this video we're going to talk about trig. So there's a lot of trig we could cover. We will cover enough trig today so that when we see trig later in calculus we will know how to use it. So we won't need to know everything about trig, but we will need to know some things about trig. And the things we'll need to know pretty well in order to use them in calculus. But fortunately, the things we need to know are not many, but we do need to know them well. So first, let's talk about radians. No, first let's talk about how trig functions are defined, and then we'll talk about radians. So trig functions are defined to be ratios of sides of right triangles. So here we have a right triangle. Here we have an angle, let's call it theta, and we have three sides on this right triangle. This one is called the opposite, because it's opposite the angle. This is called the adjacent, because it's right next to the angle and not the hypotenuse, and this is called the hypotenuse. And these sides and this angle will define 6 trig functions. So define sine of an angle. So trig functions take as their inputs angles. Sine is defined to be the ratio of the opposite side to the hypotenuse side. So the opposite side length, whatever that is, divided by the hypotenuse length, whatever that is. And we'll abbreviate that O over H. Cosine of theta, remember our angle theta is over here, it's this angle. So sine of theta is opposite over hypotenuse. Cosine of theta will be the adjacent over hypotenuse. And we'll call that A over H. Tangent of theta, that's an H, not an asymmetric H. Tangent of theta is defined, well actually, in its most basic sense, tangent is defined as sine over cosine. But in the triangle, we can see that as the opposite over the adjacent. And of course, we'll just make I'll make that remark in a moment. You might have just heard a loud car driving by. So I'll repeat what I said, but I forgot what I just said. So right here, tangent with this triangle is defined as opposite over adjacent. It's also the same as sine over cosine, and I'm not going to write that here. I'll write that in an alternative definition. Right here, I'm just going to stick with these sides of the triangle. So here we have 3 functions, and the other 3 functions are just their reciprocals. So the reciprocal of sine is called cosecant. And cosecant is the reciprocal of sine. So flip that around. Cosecant is spelled C-O-S-E. Maybe I should spell these. Sine is S-I-N-E, abbreviated S-I-N. Cosine is C-O-S-I-N-E, tangent T-A-N-G-E-N-T. Cosecant, C-O-S-E-C-A-N-T. And that's the reciprocal of sine. So it's 1 over sine, but with the triangle, 1 over sine is just the fraction flipped around, because that's what a reciprocal is. Secant of theta, S-E-C-A-N-T, is the reciprocal of cosine. So that's hypotenuse over adjacent. And tangent, and cotangent, abbreviated C-O-T, cotangent, C-O, tangent, is the reciprocal of tangent. Adjacent over opposite. And of course that's the same as cosine over sine. So right here we have these definitions. We will use these several times. We'll see these several times. My eraser's down here. So first, let's keep these in mind. So right here, the definition started with a right triangle and an angle in the right triangle. Another way of defining them, and we'll use this as well, is using the unit circle. So I'm going to draw something and then we'll talk about it. So the unit circle is a circle of radius 1 centered at the origin. Pretend that's centered at the origin. Well, I shouldn't command you to pretend. I request that you pretend that's centered at the origin. I'm going to label a couple points. It's radius 1, so this point up here is 0, 1. This point over here is 1, 0. These are what? 0, negative 1, negative 1, 0. I'm not going to label them for now, because right now we're going to focus in on the first quadrant. There is a right triangle touching this unit circle, like this. So there's a right triangle. The hypotenuse is 1 because it's a unit circle. Now, this ordered pair, well, it is an ordered pair, so it has an x and a y. But we can tell something about this x and a y because of this being radius 1. What can we tell? Well, let's remember sine of theta is opposite over hypotenuse. Cosine, we'll just keep these in mind, is adjacent over hypotenuse. We need to know those. And right here, this angle we can measure as theta going up like this. So we're going to start at the positive x-axis and go up for that angle theta. But right here, sine, well, let's do cosine first. Cosine is adjacent over hypotenuse. Hypotenuse is 1. Adjacent over 1 is just adjacent. So this x length on this triangle, well, maybe I should say this leg of this triangle has length cosine of theta. Okay, well that tells us this ordered pair on this unit circle starts with cosine of theta, because the hypotenuse is 1. Well, similarly, the hypotenuse is 1 in this relation, so sine of theta equals the opposite length divided by 1, which is just the opposite length. So this length right here is sine of theta. That's the length of this leg of that triangle. So that tells us the y-coordinate is sine of theta. So right here, any point on the unit circle off of the axes will define a triangle. And that triangle will have ordered pair cosine of the angle and sine of the angle. Now, one observation I'd like you to make with this is, well, it's slightly off topic. Well, it's not off topic. It's slightly not exactly in the order of how things should potentially be used or be described. But I would like to make an observation here because we will use it in this course. Right here, we have a right triangle, so the sides will satisfy the Pythagorean theorem. So observe. Let's observe it a little higher on the chalkboard. Observe. Those sides satisfy Pythagorean theorem. What's Pythagorean theorem? Pythagorean theorem is this squared plus this squared equals that squared. So sine squared theta plus cosine squared theta equals 1 squared. So we have this nice relation, a very important relation. Well, that's a nice relation. Can we use it to get any others? Yes. And the fact that I moved it up on the board should have given you that answer as a hint, or should have given you a hint toward that answer. What can we do with this relation? Well, there are a lot of things we can do with it. Let's do 2 things to get 2 similar relations. So divide, let's spell divide right. Divide this entire equation by, how about cosine squared? So let's take that entire equation, divide it by cosine squared. Well, first part we have sine squared over cosine squared. I'll say we get sine squared over cosine squared. That's tangent squared, because sine over cosine is tangent. Divide this by cosine squared. Cosine squared divided by itself is 1. So we have tangent squared plus 1. Divide the other thing by cosine squared. You get 1 over cosine squared. I'm going to erase that and write it a little smaller. Or, yeah, smaller. So we divide the entire equation by cosine squared. Sine squared divided by cosine squared is tangent squared. Cosine squared divided by itself is 1. 1 over cosine squared is secant squared, because the reciprocal of cosine is secant. So to see that on the left side, how would you see that? 1 over cosine squared of theta equals 1 over cosine of theta, all squared by exponent properties. 1 over cosine is secant, because secant by definition is the reciprocal of cosine. So that's secant squared on the right side. With trig functions, when you square a trig function, it's typical to write it with the square like that, rather than having to write the parentheses and the square like that. That's just a notational shortcut that exists for trig functions. It doesn't exist for logarithm functions. I'm not sure why, but it doesn't. The only thing I could think of for why has something to do with the logarithm properties. But let's erase this, since if you want to see it again, you can rewind the tape. And let's write another relation. Well, we divided everything by cosine squared. What if we divided everything instead by sine squared? Divide everything by sine squared. Well, sine squared divided by itself is 1. Cosine squared divided by sine squared. Well, that's tangent squared, but flipped around, because cosine is on top. Tangent flipped around is cotangent. And on the right side, we get 1 over sine squared, which is cosecant squared. So I will not ask you to prove these relations, but it is common to see a list with these 3 equations. I find this one quite easy to remember. I find these 2 very difficult to remember. Like, they have ones and tangents all over the place and reciprocals of trig functions. I think there are a lot of places to get confused with these 2. So whenever I need to figure out these 2, which will probably happen sometime in this course, we'll probably see these show up. Whenever I have to use them, I usually just start with this and write out the division. For those of you who are taking Calc 2, there's a thing called doing an integral by trigonometric substitution. And knowing these relations very quickly helps understand that quite well. Sometimes when the board gets used a lot, Windex helps. Or great value glass cleaner, original fresh scent. It's actually Windex in a great value glass cleaner bottle, because I don't like Windex bottles for some reason. The handle I don't think works that well. Okay, so these relations are good to know. But what other trig do we need to know? Well, we have angle measurements by degrees. Using degrees is not always useful. As a matter of fact, in math, using degrees is very unuseful. So instead, we have another measurement. And to define this other measurement called a radian, we will start again with the unit circle. Degrees measure angles. The measurement we're going to concern ourselves with is, well, here's the unit circle. Here's an angle. Again, we're measuring in that direction from the positive x-axis. The question is, we would like to use that piece of the circle. We'll use an arc of the circle. And we want this angle to correspond to this length. We'd like a relation between this angle and that length. Well, we know, this is a unit circle, we know very conveniently the circumference of a unit circle. We also know that a circle has 360 degrees. What's the circumference of a unit circle? The circumference of a circle is 2 pi r. Yes, 2 pi r. Unit circle has radius 1. So circumference of unit circle is 2 pi times the radius. 2 pi times 1, which is 2 pi. Well, a circle, the angle that defines a circle has 360 degrees. And we're going to use this standard to define a radian. We're going to define the radian to relate the circumference of a unit circle to the angles in a unit circle. So how do I want to say that? Well, let's just say it. Define the radian Radian to relate these two. So 2 pi radians equals 360 degrees. So we have a conversion factor. 2 pi radians is 360 degrees. Cancel out a 2 on both sides. Pi radians equals 180 degrees. So if you have an angle in terms of degrees and you want it in terms of the piece of the length, or the length of the arc instead on the unit circle, well, we can use this. So let's do a couple conversions first before working with radians. Let's see how the conversion works. So this will be convert these to radians. Let's do let's do 2 of them. Example. Convert to radians. We'll do 2 parts. Let's do 30 degrees, and let's do negative 73 degrees. That's a good number. Let's do it over here. Well, all we need is this relation. And we can use division to our advantage. So first for 30 degrees, well, we have 30 degrees. So if we want to cancel degrees and be left with radians, we'll divide by degrees and multiply by radians. So pi radians divided by 180 degrees. So here degrees are going to cancel, those units will cancel, and we'll be left with radians. 30 divided by 180. So right here in a computation like this, it's convenient to write the pi separately and then write the numbers in front of it. So I see this really as 30 divided by 180 times pi. What's 30 divided by 180? Well, 0, or 10 divided by 10 is 1. 3 divided by 18 is a sixth. So we have a sixth pi radians. And for simplicity, we can just write that as pi over 6, and we'll assume that's radians. This will be the last time I write the word radians. No, this will be the last time I write the word radians. So to go from degrees to radians, we use this conversion factor. It's like just like going from centimeters to inches. You have what is it? It's I don't know the metrics. I don't like the metric system. 2 point something. This could be wrong. I hope it's not wrong. 2.54, I believe it is. So, what am I thinking? If you want to convert inches to centimeters, say 12, not 12, let's do 11 inches to centimeters, you would divide by inches, multiply by centimeters. There, okay, this is a better number. 10 inches to centimeters. So if you want to convert 10 inches to centimeters, what you do is you find the conversion factor, which is 1 inch for every 2.54 centimeters, and then use division and multiplication to your advantage. So inches divided by inches will cancel, and you're left with centimeters. In this case, it's 25.4 centimeters. So inches divided by inches will cancel. You're left with centimeters. Just like up here, degrees cancel, and you're left with radians. I will not test you on converting inches to centimeters. But it's the same thing. A lot of people have done this computation in like a chemistry class. That's where I saw it. Going from degrees to radians is the same. And similarly, going from radians to degrees, you just follow the units. But we want to convert 73 to negative 73 to radians. Well, we have degrees, so we'll divide by degrees, we'll multiply by radians. 73 is a nice prime number, so this fraction does not reduce. So we have negative 73 over 180 pi radians. So we just followed the conversion. Now one other observation I'd like to make. This angle, negative 73 degrees, or this radian measurement, remember, positive angles go up from the x-axis. Negative angles are going to go down. So negative 73 degrees would look something like that, going down from the x-axis. The next thing I'd like you to observe about trig is what happens depending on the quadrant you're in. So there's a convenient diagram we can use to help us. It looks like that. Now there are a few ways of remembering this. You can remember it as always study trig carefully. That's how I was first explained it. That's kind of how I remember it now. But what we do is we use this to figure out how the trig functions, well, we use it to figure out the sine of the trig function, the SIGN sine of the trig functions when the angles are inside these quadrants. So how do we interpret this? Well, for angles in quadrant 1, so let's say for angles theta in quadrant 1, all trig functions are positive. So we'll say for angles, let's do A, B, C, and D so there aren't 1s and 2s and 3s and 4s all over. For angles theta in quadrant 1, so that's this quadrant, all trig functions are positive. Okay? What about quadrant 2? What does that S mean? S means study. Always study trig carefully. But S also means sine here. In the second quadrant, sine is positive. Sine is positive. If sine is positive, then its reciprocal is positive. And all the others are negative. So if you have an angle that's in quadrant 2, sine is positive, cosecant's positive, but cosine, tangent, secant, and cotangent are all negative. Similarly, in quadrant 3, trig. There's a second way of all students take calculus. I remembered it from trig. So T, either take or trig, depending on which mnemonic you use, means tangent is positive in quadrant 3. If tangent is positive, then cotangent is also positive. So in quadrant 3, tangent and cotangent are positive, and in quadrant 4, for carefully, C means cosine. So cosine is positive and secant is positive. So cosine and its reciprocal, which is secant, is positive. Now I think the is works rather than are because this is parenthetical. If I left the parentheses off, then I should have used are. Although I could be wrong about that. So if you know grammar and the parenthetical does carry over to the verb, let me know. I think it doesn't. So we'll use this. So let's keep this in mind right now. If you have an angle inside one of the quadrants, we can use this to figure out the sine, the SIGN of the trig function evaluated at that angle. Now that's just inside the quadrants. What happens if you're on one of the axes? Well, let's look at the axes. Well, if we're evaluating trig functions and we get an angle on the axes, so let's say, what about the axes? Well, first, let's figure out the radian measurements on the axes. Angle 0, remember, we're starting at the positive x-axis moving upwards. Angle 0, 0 degrees times pi over 180 is still 0. So this is 0 radians. Well, what about the one going up? This is a right angle. So that's 90 degrees. Well, let's convert 90 degrees to radians. 90 degrees to radians, remember it is pi radians for every 180 degrees. Degrees cancel, you're left with radians. 9 divided by 18 is a half. A half pi is the same as pi over 2. I'm going to lower this graph a little. So this one is 0. This one is pi over 2. What about this one over here? Well, that's 180 degrees. 180 divided by 180 is 1. And the pi is still there. Down here, 270 degrees. 270 degrees. 27 divided by 18, you cancel a 9, you're left with a 3 and a 2. So that's 3 halves with a pi. And over here, all 360 degrees, well, we already know that that's 2 pi. It's set up to be 2 pi. And you'll notice if you have an angle over 360 degrees, you can keep going. But for these computations, I would say if you have an angle over 360 degrees, or if you have a radian measurement larger than 2 pi, get it back down between 0 and 2 pi so that you can use our diagrams more easily. And you can do that, of course. You see here, 1 full revolution is 2 pi radians. So if you have more than 2 pi, if you have, say, this angle, whatever that angle is, you can subtract 2 pi from it and be left with an angle between 0 and 2 pi. Similarly, if you have a negative, you could get that between 0 and 2 pi. We'll see about that. Sometimes I leave it as a negative because it's more convenient if it's small negative, but we'll see. Sometimes I don't. So this is 0 and 2 pi. Sorry, something just, my throat isn't cooperating with me, so I need water. So we have these angles. Well, what if we have to evaluate trig functions here? Well, we already have the unit circle. And we have these coordinates on the unit circle. So if you have to find a trig function evaluated at an angle on an axis, you don't have to worry about sine, about going through a sine argument. All you have to do is go straight to the unit circle. And that tells you everything you need to know, because remember, the x-coordinate is cosine of the angle, the y-coordinate is sine of the angle. So here, if I asked what's cosine of 3 pi over 2, well, you'd go to the unit circle, you'd go down here to 3 pi over 2, and then you'd look at the x-coordinate. Cosine of 3 pi over 2 is 0. So let's also keep that in mind. One other thing to keep in mind before we start doing some examples of trig functions. Well, 2 other things, but they're kind of one thing. So right now we have radians. We have this ASTC diagram. We have the unit circle. There's one other thing we need to know. 2 triangles. How do I draw these? I draw them like that. I'll try to always draw them like this just to remain consistent. Of course, you could draw them backwards. 2 important triangles, which will tell us a lot of what we need to know. You'll remember from a geometry class, a 30, 60, 90 triangle has sides in ratio 1 to root 3 to 2. Well, that's fantastic, but we need radians. 30 in radians, well, we already did that as a computation earlier. It was 30 times pi over 180. And 30 over 180 reduced to 1/6. So this 30, 60, 90 triangle, we can get rid of that 30 and replace the 30 with a pi over 6. 60 we can get rid of and replace 60 divided by 180. The 10s cancel, 6 and 18 makes a third. And we get a pi over 3. So we have this triangle. The 30, 60, 90 triangle in radians. This will be helpful. The 1 goes opposite the 30 degree angle, which is the pi over 6, because 1 is smaller than root 3. Root 3 is like 1.7 something, and 1 is 1. The other triangle that's useful is the 45, 45, 90. And you'll remember from a geometry class, the 45, 45, 90 triangle has sides in ratio 1 to 1 to root 2. Now 45 in radians is what? pi over 180. 45 into 180, that does work nicely because 90 times 2 is 180. So 45 into 180 is 1 into 4. So we can replace these 45s with pi over 4. So we have a pi over 4, pi over 4, pi over 2 triangle with sides in those ratios. And we have 30, 60, 90 triangle, a pi over 6, pi over 3, pi over 2 triangle with sides in those ratios. So right now we have everything we need to know to do the calculus, well, to do the trigonometry we could see in our calculus class. So let's do a few examples. My pages fell several times, now they're out of order, so I have to find where I am, because I want to do these exact examples. So let's do some examples. So before doing these examples, I'm just going to draw a couple things on this last board for reference. Whenever I have to do trig, I draw these. So I'm 28 years old. I've done calculus. Let's see, my senior year in high school I did it. So what's that, 10 years ago? 11 years ago? Something like that. 10 years ago. No, 11 years ago. So I've done calculus. I did pre-calc before that. To this day, when I have to do something like this, tangent of 2 pi over 3, I draw this on the side of the board, or on the side of my paper, for reference. Let's draw it a little better since this is on camera. I should probably draw it a little bigger so that it's visible on camera. My chalk is getting small, and I'm hoping to not have to use another piece. So whenever I have something like that, I draw this on the side to help me not make a mistake. I also draw this if I need it, which we will need it in a moment. I also draw that. I also I don't draw this. I mean, at the beginning, for the first few of those years, I did draw this. But now I don't. But and some of you might be seeing trig for the first time, so I will draw this for now. Whenever I have to do trig evaluations, I draw them. So let's do a couple. Let's do 3 of them. Evaluate these. Secant of 3 pi over 4 and cosine of 7 pi over 2. That's a terrible tune. And cosine of 7 pi over 2. So let's do these. Now to do these, all you need are a sine and a reference angle. The reference angle you can find just by looking at what you have and this triangle. The sine, the SIGN, is given by this. So all the work we have to do is on this angle. Well, where is angle 2 pi over 3? Which quadrant is that in? Well, maybe that's not obvious. So let's draw something that I already drew on the board. Maybe I should have just drawn that a little bigger. I'll do that. That's okay. That'll not screw up the spacing. Let's draw that ACTS thing bigger. Let's draw it and label the axes. So here is angle 0 and angle 2 pi. Here's angle pi over 2. Here's angle pi. Here's angle 3 pi over 2. So where is angle 2 pi over 3? Well, we can look at that just by ignoring the pi's and looking at the numbers. So ignoring the pi here, we have 2/3. Where is 2/3? Well, is 2/3 between 0 and a half? No. If you have 2/3 of a dollar, that is more than half of a dollar. Is 2/3 between a half and 1? Yes, it is. Which tells us that this angle 2 pi over 3 is in quadrant 2. Well, it's in quadrant 2. We have tangent. Sine and cosecant are positive in quadrant 2. Tangent is not sine and tangent is not cosecant. So tangent is not positive in quadrant 2. Which means this answer is going to be negative. Well, the only other thing we have to do is look at a triangle. And the way we can work through that is by simply looking at this denominator. That denominator is a 3. So we go to this triangle. Tangent of this angle is what? Tangent is opposite over adjacent. Opposite is root 3. Adjacent is 1. So let's write that. Opposite over adjacent. So there's our answer. Negative because it's in quadrant 2. Root 3 over 1 from looking at this angle in that triangle and using the fact that tangent is opposite over adjacent. Now, negative root 3 over 1 written like that, I don't like how that looks. So I'll just simplify that as negative root 3. And let's, so negative root 3. So we have trig function, we need the sine using this diagram, and we need the triangle. Secant. Well, let's do secant. That wasn't negative down here in the third one. Let's do secant of 3 pi over 4. Well, 3 pi over 4. Ignoring the pi's, we have a 3/4. 3/4 does not lie between 0 and a half. 3/4 does lie between a half and 1. So this is a second quadrant angle as well. In the second quadrant, sine and cosecant are positive. So in the second quadrant, secant is not positive, because secant is the reciprocal of cosine. So secant in the second quadrant is negative. Okay, that's half of our answer. The other half is done by looking at this denominator. And here we have a 4. Well, this triangle has an angle with a denominator 4. So we want secant. Well, what is secant? Well, here's our angle. Let's mark the angle first. Secant is what? 1 over cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent, because it's that flipped around. So we want secant of pi over 4. We want hypotenuse over adjacent of pi over 4. Well, hypotenuse is root 2. Adjacent is 1. So we have root 2 over 1 from the triangle. We have negative from the quadrant. And of course, this simplifies to negative root 2. Notice, this is a very symmetric triangle, so we could have used that angle as well. It's the same. And it's not a coincidence that that's the same. So in both of those first two examples, we identified the quadrant, and then we used the triangle. Now that works when the angle lies inside a quadrant. Well, what if the angle does not lie within a quadrant? Well, here's an example of that. 7 pi over 2. So if you have anything that's a multiple of pi over 2, it's going to lie on one of the axes. If you have a whole number pi, it'll lie on the x-axis. If you have a pi over 2 that isn't a whole number, it'll lie on the y-axis. 7 pi over 2. 7 halves. That's 3.5. That's much larger than 2 pi. So let's first deal with this by making this angle lie between 0 and 2 pi, because then we can go over to this diagram or a unit circle. I'm going to erase the examples above right here and do this one up at the top. So we have what? Cosine of 7 pi over 2. Well, 7 pi over 2 is larger than 2 pi. So let's subtract 2 pi. In other words, let's go one fewer time around the circle and see if we lie between 0 and 2 pi now. Well, let's get a common denominator. Well, there's our common denominator, 2. 7 minus 4 is 3. So the angle 7 pi over 2 results in the same, at the same endpoint on the unit circle as the angle 3 pi over 2. So cosine of 7 pi over 2 is the same as cosine of 3 pi over 2. Well, using this diagram, 3 pi over 2 is down here. So all we need is the unit circle to figure this out. So using the unit circle, let's draw that. I've drawn the unit circle a lot of times. I wouldn't be surprised if I've drawn the unit circle like that 1,000 times in my life. So where am I? We want cosine of 3 pi over 2. So here's the point on the unit circle at where angle 3 pi over 2 hits. Cosine of 3 pi over 2 is the x-coordinate, which is 0. If this question said find sine of 7 pi over 2, it would be -1, because that's the y-coordinate. But we have cosine of 7 pi over 2, which is the same as cosine of 3 pi over 2, which is 0 from the unit circle. Let's do one more example. So let's add a fourth part to that previous example. Let's do 2 more examples. Let's do cosecant of... No, let's do 3 more examples. Yeah, I'll erase this. Let's do sine of 4 pi over 3. Let's do cosecant of 4 pi over 3. And let's do cotangent of negative pi over 2. Let's start with the first one, because it's first. That's faulty reasoning. Just because something is first doesn't mean that's the one you should start with. I very frequently in my classing started tests on the last question. But let's start with the first one here, because I put them in this order on purpose. Sine of 4 pi over 3. Well, let's draw this thing. 4/3. Well, 4/3 is not between 0 and 1/2. 4/3 is also not between 1/2 and 1. 4/3 is between 1 and 1 1/2. 4/3 is what? Like $1.33. 1 1/2 is $1.50. $1.33 is less than $1.50. So this is in quadrant 3, this angle. in quadrant 3, sine is negative. So we have a negative. 4 pi over 3, well, let's go to the triangle with angle pi over 3. Right here. It's already labeled for us. Sine of pi over 3, sine is opposite over hypotenuse. So that's not the opposite that I pointed at. Sine is opposite over hypotenuse. Sine of pi over 3 is root 3 over 2. So we have negative root 3 over 2. Now let's do cosecant. Well, you could go through the same type of reasoning we just went through if we didn't already do this problem. Since we did that problem, we don't have to do much work. Because remember, cosecant is just sine flipped around, the reciprocal of sine. The negative doesn't change by that reciprocal. The negative stays the same, but the numerator and denominator flip around. Now, if you didn't make that observation that we did a lot of the work for us up here, you could go through this reasoning. The angle is in quadrant 3, so cosecant is negative. You go up here, and cosecant is what? Hypotenuse over opposite. So you get negative hypotenuse over opposite. Now let's look at this last one. Cotangent of negative pi over 2. Now sometimes when you have a negative, I think it's convenient to turn it into an angle between 0 and 2 pi. But sometimes I leave it alone. And this is a case where I leave it alone. And the reason I leave it alone is because negative pi over 2, well, there's angle 0. Angle pi over 2 is straight up from 0 at the positive y-axis. So negative pi over 2 is the same thing, but in the opposite direction. Negative pi over 2, of course, is the same as 3 pi over 2. You could add 2 pi to it. But with negative pi over 2, I usually just leave it alone. So now we need cotangent of negative pi over 2. Well, let's remember what cotangent is. Cotangent is tangent flipped around. All we have on this ordered pair is information about sine and cosine. We know sine of negative pi over 2 is negative 1. We know cosine of negative pi over 2 is 0. That's all we know. So to figure this out with what we have, we need to turn this into sines and cosines. Can we do that? Well, yes, we can. And let's explain on the side over here how we can do that. So I'm going to be informal. I'm not going to write like cotangent of theta, because that'll get in the way. Remember, cotangent is 1 over tangent. And that'll equal something else. But remember on the side that tangent of theta is sine over cosine. Tangent is sine over cosine. So cotangent is this flipped around. So cotangent is cosine over sine. So if we want cotangent of negative pi over 2, well, all we have to do is find cosine of negative pi over 2 and divide it by sine of negative pi over 2. And we have both of those numbers by the unit circle. Remember, cosine is the x-coordinate, sine is the y-coordinate. So it's 0 over 1, which is a fraction that reduces to 0. So in calculus, the trig we will see is largely based on evaluating these. When evaluating them, I keep a few things in mind. I keep those two triangles, those aren't triangles anymore. I keep the triangles that were under here in mind. The pi over 6, pi over 3, pi over 2, and the pi over 4, pi over 4, pi over 2. I very frequently draw those on the side of my paper. I also keep the unit circle in mind, in case the angles wind up on one of the axes. I also keep that ASTC thing in mind to keep myself organized with my quadrants. With all of those very precisely understood, you will not make a mistake in calculus with trig functions evaluated at points. So it's definitely worth spending some time just looking at those four things and making sure you understand them. The triangles, the ACTS, ASTC, the unit circle. I guess that's three things. So it's very important. And I guess the ratios, that'd be the fourth thing. Very important. And it's very useful to have them quickly in mind, because I mean, the only other way I've heard of to do trig is to memorize a bunch of ordered pairs, which, I mean, maybe I could have done it 10 years ago. I didn't. But I don't think I could do that now. I'm pretty bad at remembering left from right, let alone 20 different ordered pairs. Now, the last thing I'll mention about trig is just their graphs. They'll show up a couple times. Actually, I'm not going to mention their graphs. I'll do them at the beginning of next week, their graphs. Let's leave the trig discussion today at the triangles, the unit circle, and the ratio.